In this presentation, I'll be going through CVE 2014-0160, better known as Heartbleed. My presentation agenda includes providing an introduction and background information on Heartbleed, providing the timeline of events, discussing the vulnerability, then going through a proof of concept on how to exploit the vulnerability, and lastly, looking at how it was remediated. I also have a page of resources at the end with the articles and tools I used. What is Heartbleed? Heartbleed was a critical vulnerability in OpenSSL's implementation of the TLS heartbeat extension. I'll explain what a heartbeat is shortly, but essentially a heartbeat process is where regular messages are exchanged between a client and a server to keep the connection alive. The heartbeat vulnerability, also known as Heartbleed, allowed attackers to read server memory, potentially exposing sensitive data. Heartbleed was discovered in 2014 by researchers at Codenomicon and Google and affected OpenSSL versions 1.01 up to 1.01f. At the time, the vulnerability was given a CVE score of 5, which was a medium. However, later with CVSS version 3, the score was reassessed as 7.5, which is high, due to the updated scoring system, which placed greater weight on the ease of exploit. When the attackers sent a malformed heartbeat request, they were able to extract up to 64 kilobytes of memory per request. The malformed request exploited improper bounds checking in the heartbeat program. CVE classifies this vulnerability as an out-of-bounds read, CVE-125. But more specifically, the relevant classification here is buffer overread, CVE-126, which is a child category of CVE-125. Now that I've given an overview of the Heartbleed vulnerability, let's take a step back and look at the original purpose of Heartbeat in TLS. So, what is a heartbeat? Heartbeat was designed as a lightweight mechanism to keep a TLS connection active without requiring renegotiation, essentially a keep-alive mechanism for secure connections. This functionality was built into OpenSSL's implementation of TLS 1.2 and earlier versions. In many versions, Heartbeat was enabled by default. If both the client and server supported Heartbeat, they would exchange regular Heartbeat messages to maintain the connection without interruptions. Since the release of OpenSSL version 1.01 in March 2012, which introduced the Heartbeat function, to its public disclosure in April 2014, the Heartbleed vulnerability was actively present. During this period, undetected data breaches could have occurred, as the exploit left no clear traces. Nevertheless, estimates suggest that the Heartbleed vulnerability had a far-reaching impact, affecting 24 to 55% of popular HTTPS websites. This flaw exposed sensitive data stored in memory, including usernames, passwords, session cookies, private keys, and other critical information. Exploited memory leaks left no trace, so it remains unclear how much data was actually stolen, and many organizations were reluctant to disclose potential breaches. Since OpenSSL was widely used, Heartbleed impacted not just websites, but also VPNs, email servers, and databases across various industries. The severity of the issue led to global panic as companies scrambled to patch systems, revoke and reissue SSL or TLS certificates, and mitigate potential security risks. The financial impact was staggering, with losses estimated in the hundreds of millions of dollars due to remediation efforts, security investigations, and operational disruptions. In February 2012, the Internet Engineering Task Force, or the IETF, published RFC 6520 defining the TLS heartbeat extension. An RFC, or a request for comment, is a formal document that sets Internet standards, protocols, and guidelines. In this case, RFC 6520 outlined the heartbeat extension's design, functionality, and configurations within TLS. It included security considerations, recommending that malformed heartbeats from attackers be silently discarded. However, just 1 month later, in March 2012, OpenSSL version 1.01 was released, with the Heartbleed extension enabled by default. OpenSSL failed to enforce RFC 6520's recommendation to discard malformed Heartbleed messages, mistakenly processing them and causing the Heartbleed vulnerability. Then, in April 2014, researchers publicly disclosed the Heartbleed vulnerability. In response, OpenSSL released a patch version disabling Heartbleed by default. Finally, in August 2018, when TLS 1.3 was finalized, it completely removed the Heartbleed extension, ensuring that similar vulnerabilities would not exist in future TLS versions. This image illustrates the normal usage and malicious usage of Heartbleed. The intended Heartbleed mechanism works like this. A client sends a payload, such as the word bird, and states its size, in this case 4 letters. The server responds by echoing the same payload, bird. In contrast, the malicious usage of Heartbleed would work like this. An attacker can send a malformed request, which falsely claims that the size of the payload was greater than what was actually sent. So in this simple example, the client sends a payload of bird, but says that this is a 500-letter word. The server, trusting this input, returns 500 letters from whatever data is in its memory. This could expose passwords, encryption keys, and other confidential information stored in memory. There's just one thing to note about the previous example. The example is simplified, and the payload size is measured in letters, but in reality, it is defined in bytes. On this slide, you see a snippet of C code from OpenSSL's Heartbleed extension. The core vulnerability lies in the highlighted line, which uses the memcopy function. So let's see how this vulnerability happens. First, the sender transmits a Heartbleed message containing a payload, random padding, which is just extra data for security, and the declared payload size. The receiver then stores this data, in this case in P1. Next, the receiver prepares a response by allocating memory using OpenSSL malloc. This allocated buffer includes space for the response type, the payload length, the actual payload, and the random padding. A pointer, BP, is set to reference this buffer, BP equals buffer. The response message is then structured. The type is marked as TLS1 HB response, and the payload size is stored in the next line. So the critical issue occurs in the highlighted line. The memcopy function copies the payload from P1 into the allocated buffer. Memcopy requires 3 inputs, destination, source, and size, meaning it copies a specified number of bytes from P1 to BP with the size defined by payload. But here's the problem. There's no input validation. The code blindly trusts the sender's declared payload size without checking if it matches the actual data. If an attacker exaggerates this value, the receiver copies excess memory, potentially leaking sensitive information. So how do we prevent this exploit? Through input validation. If the declared payload size exceeds the actual received data, the response should be discarded to prevent unintended memory exposure. After memcopy, BP moves forward, preparing to add padding, and the memory is sent back to the sender. But if an attacker exploits this flaw, the response can include unintended data, resulting in a buffer overread and potential data leakage. Why does the sender need to specify the payload size? Why not just send the data without it? Messages don't just contain the payload. They also include minimum 16 bytes of random padding. Padding is included because it enhances security by making it harder to distinguish the actual payload. Since the padding length is random, the receiver needs to know the payload size to correctly separate the data from the padding. In short, if the sender doesn't state the payload size, the receiver wouldn't know where the payload ends and the padding begins. The proof of concept for this exploit involves scanning for open HTTPS ports, checking for Heartbleed vulnerability, sending a malicious payload to extract memory, analyzing the leaked data for useful information. To test this exploit, I used BWAP, which stands for Buggy Web Application, a test web app designed for security research. It demonstrates the exploit, which I'll walk through next. So first, you can conduct a port scan of the target machine, looking for open HTTPS ports. A program like Nmap could be used. Here, we have found an open HTTPS port on port 8443. Once you have found your open port, you then need to check if that HTTPS port is susceptible to Heartbleed. This can be done using an Nmap script, which sends a single malformed heartbeat request and detects whether the server responds with unintended extra data. Once we have found a vulnerable port, we can use a Python script to send a number of malformed heartbeats to repeatedly extract memory. Each heartbeat can extract up to 64 kilobytes from memory at a time, but we can keep sending multiple heartbeats to retrieve more data. Instead of a full screenshot, which spans multiple pages, I've included a portion of the output, but you can see the random data extracted on the right side of the output. By scrolling through the extracted output, I was able to find several key pieces of information, including a PHP session ID and the username and password for the admin account I used to log into the web server, both exposed in plain text. The recommended mitigation for an out-of-bounds read, as outlined by Common Weakness Enumeration CVE-2014-0160, is input validation. To address the Heartbleed vulnerability, OpenSSL released a patch version that implemented a validation check to ensure that the state to payload size does not exceed the actual received data. And it also disabled the Heartbeat extension by default to reduce the attack surface. On this slide is an example input validation added to prevent buffer overread. This line ensures that the expected total message size does not exceed the actual data received. If it does, then the request is silently discarded. On the left of the greater than sign is the expected total message size, including headers, the declared payload, and random padding. On the right of the greater than sign is the actual data received, the rrec.length. While the code change patched the vulnerability, organizations had to take additional steps because detecting breaches was difficult due to limited logging of heartbeat requests. To restore trust, many HTTPS server owners revoked and reissued certificates as there was a risk that private keys had been exposed. Similarly, affected websites advised users to change their passwords in case login credentials had been compromised.